Okay, so last class we talked about projectile, and we learned that projectile has like two acceleration, one in horizontal direction, another one is in vertical direction. Horizontal direction is 0 and vertical direction is, as you can see, that's number gonna be for the vertical direction. So let's watch here. So by looking at the difference in velocities at all points between 2 points, you can see all these are pointing down as shown in this animation. Okay, so that's the, remember, tail to tail and then from tip of uh, initial to final. So that's how it's doing, and that's the change in velocity. And since this change in velocity for each of the second, it's going to be acceleration as well. Okay, so that's what we learned about projectile motion. And then now, since the acceleration is constant, we can use kinematic equation. Okay, for both horizontal and vertical direction separately, but time is the same for both horizontal and vertical motion. Okay, so that the projectile. And then we started talking about Newton's laws of motion, right? Newton's first law and Newton's second law. So here is a question for you, okay, based on what you learned last time. And you have, let's say, 1 minute to answer this. So you want to respond to this based on what you learn about Newton's first law of motion. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So we are getting no and yes, mostly no, but some yes. So if I'm not paddling the wheel of a bicycle, it slows down and it stops. Looks like I need force to keep it moving with constant velocity. So if you think A is incorrect, why is that? Can you explain that?
Wouldn't it be Newton's first law? If an object is moving at constant velocity, it'll stay at constant velocity, and something acts against it to stop it. And if it's not moving, then it won't move unless you put a force on it to make it move. So wouldn't it be no? Because like if it's moving at a constant velocity, then it wouldn't need constant force because it would be Newton's first law. It would just keep on going unless something acts against it to stop it, right?
Yeah, Newton's first law says you don't need to keep applying force to keep something moving at constant velocity. That's right. But when I'm riding bicycle, I need to keep on pushing the pedal. Why is that reason then?
Because on a bike there's friction.
Right. So there is friction that's opposing, right? So because of that, what happens is in our daily life, unless we can remove friction, we need to apply force. But based on Newton's first law, if there is no friction, then we don't need to keep applying force. So that's why we need to talk in terms of net force. And that's when adding force using vector method comes in, right? So that's Newton's first law. And how about this question then? And you have total 1 minute for this one as well. Okay, 20 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. Okay. So this is moving to the right. So net force must be to the right. Is there anything wrong with that statement? Since it is moving to the right, the net force also must be right, although it is moving with constant velocity. Is my statement correct? Yes or no? Why? All I hear is silence.
Are you asking
Would it
if-
be correct? Because since the boat is moving towards the right, that means the force acting upon it going towards the right is greater than the force going against the left. So net force would be totally going right? If that makes sense.
That's what I'm trying to say.
Yeah.
And you think that makes sense, right?
Yeah.
Anybody else for whom it doesn't make sense?
Well, for Newton's first law, if it's constant velocity, then the net force is also zero.
Yeah, and there is Newton's first law. There is what we see in every day, and there is Newton's first law, right? So Newton's first law says constant velocity means net force is zero. Now there is confusion, isn't it? So constant velocity means net force is zero. So this right direction, the force on the right is just overcoming the friction from the, let's say, water where boat is going. We say that drag force, but it is like a friction, okay? A kind of friction from the fluid, which we'll talk soon, I think next week. So yes, we always get confused with Newton's first law, although it seems like very simple thingy, but we keep on getting confused, okay? So that's why I keep on bringing this kind of question a lot, okay? Constant velocity means net force is zero, okay? So it's like a bike pedaling to the bike. So this force from the wind here is like we pedaling a bike. We need to pedal the bike because there is friction opposing the motion. Same idea here, okay? So since this is constant velocity, the net force must be zero. Force must be balanced. If force is not balanced, what happens? comes Newton's second law and says there are going to be acceleration. Acceleration means velocity is changing. Changing means not constant. Whenever net force is not zero, velocity is changing. Could be increasing or decreasing. Okay, could be increasing or decreasing, but it is changing. Okay, constant means not changing, of course. So yes, it is confusing thingy because in our daily life, uh, we feel like, yeah, we need to keep applying force. Okay, but it's because there is another force always there, drag force, friction force. So to overcome that, we need to apply force. But if we did not have that, we wouldn't be using, we don't need to use any force. Okay, we didn't need to use force. Just like once you give a push to a hockey puck in a ice, nice smooth ice, what happens? It keeps moving in the same direction with about the same velocity because friction is negligible there. So find that kind of situation is a little bit difficult. You have to make that kind of situation, but when it exists, it works. Okay, so if you go to the moon, there is no air drag. If you go to the space, there is no gravitational pull or anything like that. You give a certain speed and things keeps moving with that speed. So for example, when we send, let's say, spacecraft to the Mars is nearly 1 billion kilometer away from us. 1 billion kilometers. It takes 8 months for the spacecraft to go there. That is possible because for the most of the journey, we don't need to apply any force. It can just keep moving with constant velocity. Okay. Otherwise, there is no fueling station in between. Can you drive a car for 8 months continuously without refueling it? You cannot. But turns out the spacecraft you can. Why? Because there is no opposing force. Once you put that in the orbit and give that speed, it's just going to keep moving with that speed in that direction. You need to apply force or fire the engine only when you need to change the direction or speed up or slow down. Okay, otherwise you don't. Okay, so yes, it is very different from our everyday life. So that's why it is important that we, remember and convince ourselves so that we can apply that condition in that kind of question. Okay, so I have this very short video. If you blink, you're gonna miss. And after this, I'm gonna open the poll. So there is this pen and there is this card. This pen is driving, can apply the force on the card. Okay. First, this card is being pushed by this person. You can see the hand. Okay. So this person gives a push and see what happens. Did you guys see it, or should I show you one more time? Maybe one more time. So now comes the question. And you have a minute to answer this question as well. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So we have all the options selected, but mostly we got A. Let's say, how do we know the acceleration is towards the hand or to the right? Please?
It slows down when it goes towards the left, which means that acceleration is moving in the opposite direction.
Right. And once it turns around, what happens?
The velocity increases
That means acceleration is
in the same direction.
in the same direction. Yeah, good point, Nicole. So how is that different from, let's say, a ball thrown up? Just turn this up this way, like this, maybe this way, right? Just like this card is moving, right? Situation is exactly same, isn't it? Right? And here we said, okay, ball is, the acceleration is down all the time. And same idea there as well. Okay, so in case of ball, force was coming from gravitational pull. Here, force is acting from this fan, and looks like a fan is applying force opposite to the motion. And how do I know that? Because acceleration is in that direction. Means force gonna be also in the same direction, because force is mass times acceleration. Whatever direction acceleration is, that's gonna be the direction of net force. And this thing here has friction very small. Okay, very small friction. This track has very small friction, so the net force is mostly coming from the force from the fan, and we can tell the force must be acting this way. Okay, so is acceleration changing or constant? That may be another question, right? So in this case, is the acceleration changing or constant? And another is how the motion diagram of that card gonna look like. And if we were to plot position versus time graph, how it's gonna look like. If we were to plot velocity versus time graph, how it's gonna look like. So here looks like I have only the position versus time graph and motion diagram. So let's watch this animation here. Slowing down and then starting back. Oh, my bad. So this looks like a ball you threw from here, and let's say this was up. Let's say this was up. That's what it looks like, right? So it starts with starting velocity, and then what happens? It slows down, it stops, and turns around, just like the pan card. Okay, same idea. So the position graph at the beginning, slope is larger, means velocity is high. And here, when it's turning around, slope is 0. Velocity is 0. So if you were to plot velocity versus time graph, at the beginning, velocity going to be higher and then going to decrease. And once it turns around, it's going to be negative. Just like we did for the, the position velocity graph for the ball thrown up. It's the same idea, same situation, right? So acceleration is constant in this case, although it's kind of hard to measure and tell. But once you plot velocity versus time graph and you see constant slope, right, a straight line, that means acceleration is constant. So again, object is accelerating when you apply force. That means position graph gonna look either curving down or curving up. If it is accelerating, then what's going to happen at the beginning from it? If it was just accelerating, then it would be curving up. Slope would be increasing, right? Once it starts going backward, what do you see? See, this thing is, although it may look like curving down, but what's happening here is slope is increasing as it, returns. For example, slope is increasing again, but it is pointing negative. Slope is negative in this region. Slope is positive in this region, decreasing. Slope is negative and increasing. So that's what's happening. And you can see velocity is increasing at its moves once it returns. And at the beginning, velocity is decreasing, it's slowing down, as indicated by shrinking distance between the dots that represents the motion diagram. Okay, so basically the projectile motion, or let's say the ball thrown up, was the motion. This is acceleration motion, where force is force of gravity, where the acceleration was g. Right? We said the acceleration of the object that's thrown is g. So that means by using Newton's second law, we can tell force acting on the object due to gravity is m times a, and a being g is m times g. Right? So now with the Newton's second law, we can say, okay, that's mg, and that's what we call weight. Okay, force of gravity, that's what we call weight. So that comes from Newton's second law. So we went up to Newton's second law last time. Now let's talk about Newton's third law. So Newton's first law and second law was, describing the motion. What happens when there is net force 0 versus net force not 0, let's say. Most practical way, we can think something like that. So now this third law says the interaction between two. So if I apply force in one object, what another object is doing. If you slap a person, which I'm not suggesting you should do or you do, okay? But if you slap somebody, oops, you are slapping me, I'm gonna hit you back, right? So that's how it goes. But before, even if that person doesn't do that, what's happening is this is already hitting you back. So yes, from here it may not feel like it. Try doing, or let's say, you have table, desk, something there, right? Or even wall. Try hitting slowly, just a little bit, okay? I'm banging on the table, and do a little, stronger, go a bit harder. Do you feel the difference? If you are gentle, the floor is also gentle to you. If you go bit stronger, floor is now also hitting stronger to you. Did you try already? Did you hit on something? Go ahead. Don't start with very hard. Go gentle first, okay? And try a bit harder. And see the reaction from that object, floor, your desktop, okay? What happens? Harder you hit, it hits back with the harder force. So that's what Newton's third law is. Okay, that's what Newton's third law is. So for example, here there is object A, there is object B. So object A is now going and gonna hit B. So we may say, okay, in our daily language, we may say, okay, B gets hit by A. But in reality, what happens? B hits back to A with the same amount of force. Hits back means these two forces are opposite in direction, but its magnitude is same. And keep in mind, these forces are acting in two different objects, not on the same object. One force is acting on A, another one is acting on B. Do you see that? And that is very important. If both of these were acting on same, then equal and opposite force, they would cancel. And after collision, they shouldn't be moving at all, actually. But they bounce back because there is this force that acted that gives the initial velocity for the bounce. So we call action and reaction pair. And again, this is easy to remember, but in practice, when we are applying in certain situation, it could be confusing. So let's keep that in mind, that forces are equal in magnitude but opposite in direction. And this A, B, B, A, by writing those subscript, I'm trying to emphasize the fact that they are acting on two different objects. Okay, so every information, all information is there right there in this equation. Okay, so whenever you see action, there has to be reaction. Okay, and that's the Newton's third law. So this can be used, for example, by using this, we have designed a rocket, for example. So what happens? A lot of thrust coming out. So that's the action. And there is equal reaction upward. Okay, so to lift this and give large acceleration to begin with, we need large force. So that's why what happens, a lot of thrust comes in when we are lifting the rocket. Large force is needed. So for that, large reaction is needed. Where is that reaction coming from? The action, that the thrust, okay, comes out from that. So to get a lot of smoke out, you need to burn a lot of fuel to lift up. Okay, so that's why it becomes thick cloud of smoke, the rocket launch. Okay, and you may think, okay, the car is driven because there is force from the engine, but you can drive car on the road because there is push on the car from the road. If there was no push from the road on the car, then even when the engine is running and trying to move, it's not going to move. So for example, you may have sometimes, stuck in a snow, pile of snow, right? What happens? Once the wheel spins, it kind of becomes ice, friction becomes negligible, and then what happens is that the road cannot push the car. Okay, so although car is trying to push the road cannot push. So what happens? Car cannot push the road, and road cannot push the car. So because of that, you cannot drive forward. You are stuck. Okay, so it seems like, okay, it's the engine that's driving the car, but it's the road that's helping to move the car. Okay, but of course we need to push the road to get pushed back from the road. So that's where the engine and all those mechanism that transfers all those to the spin to the wheel comes in. Okay, so it's the wheel, when it's spinning one way, it's pushing road one way, and road is pushing it exactly in the opposite way, and that's how it's moving. Okay, so that's why friction matters. It's not just for car. It's very hard to walk on the ice, isn't it? You have to be very careful. You cannot go like large step, longer step while walking on the snow. You cannot. Why? When we are walking, we are pushing the floor and floor is pushing us back, and that's how we can move. If there is no push from the floor, and that's going to be the case when there is very slippery ice, then what happens? You try to push, but what happens? Your leg just slips. You cannot push on the floor. That means floor is not pushing you back to move forward. Okay, so next time you walk, what you want to do is pay attention which way you are pushing to the floor and how the floor is pushing back to you. Okay, try that. And of course, we all know nail gets hammered. But now we know hammer also gets hammered, or should I say nailed back with the same amount of force. Okay? Those are also action and reaction. Let's say if there was no air on the earth, no atmosphere, no environment, do you think the bird could fly? Let's say somehow, let's say you put some air for the breathing, like you put with the tube, cylinder and tube. Wings are free though. Do you think the bird could fly? They cannot. What happens when birds fly? They are pushing air down and air is pushing up. That's what lifting them up. Okay? Airplanes, they can lift up because air is pushing down. So probably you may have heard NASA has sent a helicopter on the Mars, and I think it's going to be landing sometimes this February. Okay, and it's going to fly on the Mars. But the atmosphere on the Mars is very thin compared to atmosphere here on the Earth. So now you have to, so what's going to happen? It's not going to lift up so easily on the Mars as it would here. But fortunately, the Mars has a smaller gravitational pull, so it doesn't require as much force to begin with. So that's a bit helpful though. Okay. And remember, it's the net force matters, not just the one force, right? So now there is large object and smaller object colliding. So which one you think gonna exert larger forces when they collide? Larger, right? Larger slams with larger force. Or am I wrong now? Force from larger block. Force from larger block is larger than force from a smaller block. Is that correct or incorrect? So I see there is no and explanation that says they have the same force. And how do we know that? Action reaction. As long as those forces are action reaction, they gotta be same, okay? Cannot be different. So in this kind of situation, we may feel like, okay, hammer is hitting harder to the nail. The large block gonna exert large force. We may think something like that, but it doesn't work that way. Okay, they are equal and opposite. So now here is a question for you. The person is pushing the car, so that means car is also pushing the person, right? It says the force from the person on the car is what? So you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, what we got here? Are you guys ready? 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 Okay. So equal, mostly, greater. Speed of car is increasing. Does it has any effect on how much force the person get from the car? We have these two choices mostly. Somewhat A also makes sense to me because speed is increasing. So shouldn't the force be greater? Can somebody help me here?
They're equal forces if because this car's speed is increasing. That doesn't really have an effect because the two forces are acting on different objects. So the net force on the car can still be positive even if it's pushing back onto the person with the same force.
Right, so push from the person may be producing acceleration, right? So so that does not mean it has to be equal, larger because they are acting in two different objects. Yes. So what does that mean then? That means looks like C is correct answer here. And whenever we say force from the person on the car and then force from the car on the person, we are talking about this action reaction pair. You see that? And as long as we know they are action reaction, we can simply say they must be equal. So that's how it comes in. Okay. Thank you, Neil, for the help. So now that's Newton's third law. So those are the Newton's laws. So we're going to be taking account of those and learning how to solve problem using that. Okay. So we notice that it's not a force or two forces that matters for the motion. It's the net force that matters for the motion. Okay. So we need to look in terms of net force. What's happening to the motion, to find out what's happening to the motion. So to find net force, what do? We draw a free body diagram. So to draw a free body diagram, we look for the all forces acting on the object of interest. So that is very important. isolate the object of interest. So in this case, let's suppose if I want to draw a free body diagram of puck, what do? This is what I do. I say, okay, my object of interest is puck. Any force not acting on the puck, I do not want to draw. Okay, so what forces are acting here? Puck is, let's say, this puck is just sitting on inclined surface. Okay, sitting on the inclined surface. It's not sliding, just sitting. Okay, inclined surface. What are the possible forces here? So I see one normal force written on the chart, and there is weight. Right, so we identify, and this is important, only on the object. Normal comes from the push where the object is sitting on, touching, right? If it's not touching anything, normal force is not there. And the weight is always there as long as we are near the earth gravitational field, because weight is the force of pull from the gravitational force, right? And see, this is inclined. If there was no friction, probably it would start sliding. It's not sliding and sitting there. Most likely means there is friction acting in opposite direction, right? So this force is there. And once you have that, you can replace object by a dot and then draw forces with correct direction by represented by the arrows. So this object, I am replacing that by a dot. And when I draw forces, this is important. Okay, we draw all arrows starting from the object, not ending on the object. So that means, and it is always a good idea to choose axis. Okay, so that way we can find component of the force if needed. So here I'm choosing x-axis along the incline. Why am I doing that? Usually it's a good idea to choose one axis along the motion. If motion is not happening, then which direction the motion would most likely happen, okay? If it were to start moving, you want to think in terms of that, okay? So in that case, what happens? This way I decide to choose my x in that direction, and could be positive x in this direction. It is easier when you choose positive direction in the direction of motion, or would be the direction of motion, but you don't have to though, okay? It makes things a bit easier, but you don't have to. You can go other way around as well, okay? So here I am drawing normal force. For normal force, I am using lowercase n, and it starts from the surface because it's coming from the surface, okay? And the weight is acting here is downward. So I'm starting from the dot, okay? And so here, this normal force, although it starts from the surface, to emphasize that it's coming from the surface, but it's acting on the object, not on the floor. We don't want force acting on the floor. We want force acting on the object. That's what the free body diagram is about. And there is friction. And although it's not moving, what happens? Friction moves. Friction acts either in the direction of, opposite to the motion, or opposite to the motion, opposite to the direction it's trying to move, right? So those ideas are going to help us to draw free body diagram. And what happens is it becomes easier to analyze the motion, add the vectors if they are just either along the x direction or the y direction, okay? So because of that, the force that's not acting either along the y or x, our choice of y or x, we find the component. So for example, W, weight is acting vertically down. It's neither along the x nor along the y. So that means we want to find its component along the y and x. Okay, so once we have component, I don't need to worry about W. That's what component means. By adding components, we get the force equivalent to the original force. Okay, so another thing is, once we fix x, y is fixed already. Y is always perpendicular to x. So you choose the x, y has to be perpendicular to the x all the time. Okay, we call this kind of coordinates rectangular coordinate. They make a kind of rectangle kind of thingy, 90-degree kind of thingy. Okay, and then of course, once you have free body diagram, then you can tell by adding forces in a particular direction, you can tell whether there is acceleration in that direction or not. Okay, net force, if the net force in that direction is 0, acceleration is 0. If net force in that direction is not 0, then there's going to be acceleration. That's what we learned from first law and the second law. Okay, and what force acting on what is very important while drawing free body diagram, right? So what may seem obvious may not be the case. So that's why I'm bringing this question here. So let's suppose the situation is like this. So now when you are looking at to solve problem in physics, right? So trying to draw free body diagram of the card, let's say, trying to draw free body diagram of the card. That means what force is acting on the card? What force is pulling the card? So that's the question here. So I'm opening the poll and you have a minute to answer this. Oh, I forgot to warn. You have around 15 seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see. Let's see. Let's see. So we have a response to all of these, but majority is for D. And I think, is D the correct answer here? Force on the rope attached to the card. So it's the rope that's pulling the card. Getter is pulling the rope. And rope is pulling card. So yeah, it may sound kind of, what are you talking about, Ramesh? It's the same thing. But remember, force from the getter is not acting on the card. So if I'm trying to make free body diagram of the card, I cannot use that force. I need to use force from the rope, okay? And that's going to be tension force. So yes, and so it may sound kind of ridiculous, but it's very important that we identify what force is acting on what properly by critical thinking on that. Okay, so one more here. So How about free body diagram of the system? System consists of the sled and portion, okay? Think about sled and portion, replacing sled and portion by a dot. Both sled and portion by a dot. And then draw free body diagram. So which one you think gonna best represent? And you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Now, are you guys ready to see which one got most vote? Which one wins? Okay, so it looks like C is winning. So just like many of you, I'm thinking C as correct answer. Am I right or wrong, and why? I'm still waiting.
I don't think it's C or D because the dog isn't part of the system, so we shouldn't count the friction from that's acting on the dog, I guess.
So D is not pulling the system. Dog is pulling rope. Is that what you are trying to say?
Um, I was thinking that the friction of the dog shouldn't be included in the diagram, the free body
Oh,
diagram, because it's not the system. It's not part of the system. Just the
okay.
sled and the kid.
Okay. So F, dog, that is a force from the dog. Maybe, yeah, I should have written that. It's not friction from the dog. But of course, dog, if there is no friction on the dog cannot apply force. It's going to be slippery, right? Um, so when we draw free body diagram, what do? We isolate the object, object of interest, right? So in this case, it's going to be the portion and the sled, and that's what the dot is. So now we look at what forces are acting there. Force from the dog is not acting on the system. Force from the dog is acting on the rope, just like we had. Alligator wasn't pulling the cart. It was the rope, tension on the rope that was pulling the cart. So that's why the force of dog shouldn't be there in the free body diagram. No, it does not belong there. Dog is not pulling the sled. Dog is pulling the rope, and rope is pulling the sled. Again, it may sound a bit ridiculous, right? But that's how we need to look. Otherwise, when we solve problem, they are going to be problem rather than solution. Okay, so it looks like B going to be the best in this case among the given diagrams. Okay, so here this also looks like reasonable. Okay, A looks reasonable, but in free body diagram, what do? We replace the object by a dot, so I'm using that. Okay, and okay, yes, so that's why B is better than A. But C and D, including force from the dog in the diagram, is not a good idea. That's wrong. Okay, so let's take a break. So we're going to be using this idea to draw a free body diagram and solve problems. So that's what we're going to be doing after the break. And I'm going to pause the recording. Hopefully, if I forget, you guys are going to remind me. Okay, welcome back, folks. So now it uses again idea of Newton's first law, second law, and free body diagram. So you need to use that information to answer this question. Okay, so I'm opening this. Since we are just coming back, I'm giving 2 minutes to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Mostly A, there is one B, and there are some D, and one E. Okay. So let's say if I'm thinking A as correct answer, why am I right or wrong?
Well, considering that there's constant velocity, would mean the net force is zero, and the net force is zero.
Somehow I lost your voice.
Oh, sorry. So I was saying that since the net velocity is constant, or rather the
I
constant.
can still barely hear you.
Oh, so
Can you come closer and speak, please?
yeah. So considering that velocity is constant would mean that net force would have to be zero because there's no friction. So diagram A would be the only diagram showing a net force of zero.
So yes, I still kind of found hard to hear you. Maybe it's my speaker, but if I got it correctly, you said velocity is constant in horizontal direction, so there is no net force. Means
Yes.
since there is no friction or a resistance that's like let's say opposing it, there wouldn't be any force in this direction, in the direction of motion. You don't need force in that direction for constant velocity, right? So that means C and D is not correct. We don't need force in that direction. Now for the C, D, B. Oops, all of them are gone once we realize that fact, right? So we are left with just A. So now let's see. A, upward force. I'm guessing that's a normal force. And downward force is the weight of the glider. And there is no acceleration up or down. That means they are equal as well. So length of the arrow, same length, makes sense too. So yes, folks, A is correct answer. Okay. So yes, we have hard time believing that there is no force in the direction of motion, but that's what Newton's first law is. Okay, you don't have to have force in the direction of motion as long as motion has constant velocity. Okay, so if there is nothing opposing, you don't need to be pulling with the, if something is not being opposed, so that's what it means, no air resistance or friction. So there is nothing opposing the motion, so that means you don't need pull force as well. Okay. So now it's time for doing some, let's say, numbers as well. Can you draw a free body diagram of elevator in this case? Pull out paper and draw free body diagram of elevator, please. Uh-oh. What am I doing here? Ha. Stuck. Blocking things. So object of interest here is elevator. So replace, just put a dot for elevator and draw forces acting on the elevator. So how many forces are acting on elevator? And which ones? Can you type that on the chat? Which forces did you draw? Tension, weight, weight and normal, tension and weight. Okay, keep coming. So far I got only 5 or 6 responses. So I'm hoping everybody drew, okay, although not responding, everybody drew the diagram. So now I'm drawing it. So elevator, there is cable attached to the elevator, and of course there was question like this, I think, on the pre-class exercise as well. So tension on the rope, and always there is weight. So mass is given. So I like to write weight in terms of mass mg. So that's what the weight is, okay? But whenever mass is given, I like to write weight mg. If whole weight is given, just that many Newton, then I'll write just W, okay? But here mass is given. So to make sure that I don't forget to multiply that by G to make it force. Mass is not a force. Weight is force. To get to weight from mass, we need to multiply by G. Remember, force is mass times acceleration, and acceleration due to gravity is G. Okay, so that's that. And how about normal? So is elevator, when it's moving up or down, is it supported by some surface? See, normal force comes from the push from surface where it is sitting on. Okay, so elevator is just hanging with the help of rope. So that's why they're not going to be a normal force here. Okay, so that's the free body diagram. But we want to choose axis. And in this case, motion is just in y direction. So we can just draw y. Okay. And we can choose up as a positive. Here, what's happening? Yes, it is accelerating up. We can choose up as a positive. So even if it was accelerating down, we could choose up as a positive. So choice up or down, whichever is positive you choose. It's arbitrary, okay? You can choose it. But once you choose it, you need to stick with it until you get the answer, okay? So here I'm saying up is a positive. So there is mass, there is acceleration, and we are asked to find a force. So force, mass, and acceleration, they are related by what law? What physics connects that? It's the Newton's second law, yes. So that means we want to use this equation. Net force is equal to mass times acceleration. And in this case, motion is y direction, just like for the projectile motion. For this one as well, we can just break. The Newton's law can be broken into x and y components and can be used independently, okay? So that's why I'm writing this like this, rather than just F is equal to ma. I'm writing Fy, sum of Fy's, that means sum of all forces acting along the vertical direction. That's what y here means, is equal to mass times acceleration in that direction. Okay, so that's how I write Newton's second law. This is formula. So now I need to translate this formula or use this formula to this particular problem. Okay, so what this means, read that as a sum of forces in y direction. And we figured there are two forces acting in y direction, right? One is tension, another one is weight or mg. So now force is a vector. Positive sign and negative sign in front of it tells us about the direction. So we cannot miss that. Okay? So that means here tension is pointing up. And we chose up as a positive. So that means tension is positive or negative? Must be positive. So although we don't need to write positive sign for the first term, but I like to write it down, especially when I'm post practicing it, so that I am making sure that I'm not missing to check the sign of the force. Okay, so that's that. And sum of two forces here, one is tension, we took care of that. Next one is mg. What's the sign of mg? Positive mg or negative mg? So mg is negative. Why? It's pointing down. And we chose up as a positive. So up positive means the force that's pointing down must be a negative. And this is equal to mass times acceleration. So mass doesn't have direction, but acceleration does. So what is the direction of acceleration? The question says upward, right? So that means although the acceleration is not a force, remember, acceleration, to make acceleration force, we need to multiply that by mass. So this whole term is force, but acceleration is not a force. And in free body diagram, we do not want to draw acceleration something like this. Nope, I do not want to do that. Rather, somewhere on the side, okay? Rather, somewhere on the side, I like to draw acceleration. That way I can see, oh, acceleration is pointing up, and I chose up as a positive, so that means this must be positive MA. See, AY is the acceleration in vertical direction, and this AY was positive A in this case. I'm assuming A is the acceleration. And what is acceleration exactly here? Value of acceleration is 1.50 meter over second square. That's what the A is. So A is value of acceleration, and it is positive in this case based on our choice of coordinate. Okay, so that's that. Now, these two terms coming from here. So always start by writing this equation, and right underneath you write sum of forces. Do that, that's the good practice, okay? And then once you're done with the left hand side, adding all forces, you move to the right hand side. Now we want tension. So that means we want to solve for T. So T is on this side, that's good. So we want to move this negative mg to the other side, right? So that means I'm moving mg to the other side, so that's why I'm not writing this anymore. But before I write mg, I may want to copy ma as it is. Since it has positive sign, since I already took care of signs, I don't need to keep on writing that positive in front of it, okay? And mg also becomes positive, by the way. So negative mg on the left-hand side of the equation, when it moves to the other side, it becomes positive. So that's how I have asked you to do the algebra. But in your school, you may have learned something like this: plus mg here, plus mg here. Nothing wrong with that. We don't need extra mess, okay? We don't need to keep writing that. Rather, just, remember, okay, when the positive, negative sign, they switch side, they switch the sign as well, okay? So that's that. Now, there is mass, and there are masses on both terms. If you like, you can do this. You don't have to, but it's a good practice. So G we know, right? So this is 2010 kilogram. A is 1.5 meter second square, plus Z is 9.8 meter over second square. Some of you may be thinking why G is not negative. Isn't G supposed to be negative? See, G is here, right? So here we are using G in combination of mass, so we are using this as a force. And by writing negative sign here, we already took care of possibility of G being negative. So G actually is not negative. G is just 9.8. It is just an alphabet that represents this number 9.8 when we are near the Earth's surface. That's what it is. Okay? So don't double count that negative thingy there. Okay? So that's why it's going to be positive here. And once you add them, multiply, you get tension. Tension is a force. Force has a unit Newton. Okay? So whatever number you are getting, you can type that on the chat so that other people can also see and verify, we are getting the same number. So I see one number. We need more than one number to verify that indeed the correct answer, right? So it looks like we are getting same number. So that means I'm guessing that is correct answer. So now here is this question. So let me open the poll, and you have a minute and 30 seconds. And make sure to draw the free body diagram. Oh, I forgot to warn. 15 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it starts. Okay. Are you guys ready? 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 Okay, so we got no A, but B, C, and D. So mostly B, then some C, and some D. Okay. So how many forces are acting on this object here? Again, two forces, right? Uh-oh. Oh, I know why. I'm trying to write on the PowerPoint for some reason. When PowerPoint is in this mode, it's not gonna write. Okay. Weight is down, tension is up, right? Is there acceleration? Is there acceleration, folks? No acceleration. That's right. B constant means zero acceleration. So now let's use Newton's law. So no acceleration means object is in equilibrium. So sum of forces along the y direction must be equal to 0. Or you can think of mass times acceleration, and since acceleration is 0, the right hand side is going to be 0, right? So now, just like before, t is positive and w is negative, right? Here it says w rather than mass, so that's why I'm writing w, and that is equal to 0, so t is w. So it looks like majority of you were right. Okay. So as long as it is moving with constant velocity, net force 0 means forces are balanced with each other. Forces are unbalanced only when there is acceleration, right? So we don't even have to go through all this. If we just recall that constant velocity, no acceleration, forces are balanced. Net force is 0, right? Net force 0 means forces are balanced. Two forces, two different direction, the value are same, right? So that's why B is correct answer. And did I? Oh, already did it. So now let's go to the elevator and watch this video here. Have you ever felt like when elevator just starting versus about to stop, you feel slightly different? Especially if the elevator, uh, goes to, several story building that moves a bit faster. It stops and, like it starts a bit faster, means accelerates a bit larger.
We're in the elevator and we're moving. We're moving at a constant speed. Acceleration 0, net force is 0. But now, watch what happens. There's a small bump. And the bump corresponded with the elevator stopping its motion. And when that happened, there was a small increase in the reading on this dial. This went up to 23. Now we know the weight is 22, but the dial went up to 23. So that tells us something. Think about the forces that act. Spring force up, weight force down. For just a second, the spring force was bigger, okay? So I'm going to ask you this question. Right when we had that bump, when it went up to 23, was the elevator moving up or moving down?
What do you think? You can respond to the chat and compare what other people are thinking. Okay. So apparent weight, what is that apparent weight? So it looks like what we weigh is not always same, especially when we are accelerating or the object is accelerating. So when we are on the elevator and elevator is accelerating, we are also accelerating. That means our weight not going to be exactly mg. We're not going to feel mg, but it's different. And whatever we feel is the normal force. That normal force is called apparent weight. Okay, so normal force is the apparent weight. Now, when is apparent force bigger than the regular weight? So when we say weight, we are talking about the weight shown by the balance when we are not accelerating. That's mg. Okay, mg is the weight when we are on the scale and the scale is not accelerating or we are not accelerating. Okay, but when scale is accelerating, and then what happens? Our weight not going to be equal to mg. Our weight is what we feel push from where we are standing. So for example, when we are standing on the scale, what happens? Yes, this is not a scale, but what happens? We push the scale, scale pushes back with the same amount of force. Harder we push, scale pushes back with the harder force, same amount of force. So when we are standing on the scale, we are pushing a scale. We are pushing the floor down. And what's happening? Floor is reacting with the same amount of force. And that reaction from the floor, what we call normal force, right? And that normal force is going to be different than the mg when something is accelerating, right? So now the question is, which of these responses you think is the correct? And you have a minute to answer this. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So we got A, B, C, D, and E, and mostly C. But we also got A, B, and E as well. So A, B with constant velocity. When it's constant velocity, what happens? We don't feel the weight change. Acceleration 0 means we don't feel that. So I guess it's better if we explain by drawing free body diagram, okay? So let's say to make things clear, I'm going to be using two situations. One, free body diagram, and the acceleration is up. Okay, and that's one. So let's write down the equation for this and see what we get. Sum of forces, and I forgot to choose the axis, positive, right? Sum of forces along the y direction must be equal to mass times acceleration in y direction, right? So in that case, it's going to be n minus mg. N is positive. Make sure we are checking the sign. Is equal to mass times acceleration. Acceleration is up, means this term going to be also positive. Just like we did the very first question where elevator was accelerating. So in that case, it was mass of the elevator, weight of the elevator. But this case, we are just, our object of interest is person, not elevator. Okay. So that's why tension force is not here. Why? Because the person is not being pulled by the rope. Okay. So that means normal force is mg goes to the other side, becomes positive, and ma is also positive. So both of these are positive. So you can see normal force is larger than mg by this much, right? So it looks like when it's accelerating up, the normal force becomes larger, means the apparent weight is larger. And that's the case in the question, right? So accelerating upward is the correct answer. Now, what would happen if it was accelerating downward? Okay. So let's make free body diagram. So forces are still acting in the same direction. What changed is acceleration. Now acceleration is pointing down. So it is always good idea to include acceleration in your free body diagram, but not on the dot, but somewhere on the side. Acceleration doesn't belong on that dot. Okay. So can you write down the equation for this? We are assuming up as a positive. So we start from here just like we did. Only difference is now that this thing is also negative, right? This thing is also negative. AY is negative A, so that means I don't need that. So N is, now mg negative goes other side and becomes positive, and MA is negative. So normal force, is normal force larger or smaller than MA? Sorry, mg. So normal force we are getting by subtracting this from mg. So mg better be larger, right? So n is smaller now. Yes, just like Sam wrote in the chat. So let's do this here. Take the m out. So from here, we already learned that your apparent weight gonna be smaller. You're gonna feel a bit lighter when accelerating down. Have you guys seen the Ferris wheel that relatively goes faster? And when you are right on the top and then you start coming down, your bucket kind of falls quickly, there is downward acceleration for a moment. And do you feel different at that time? Do you hear a scream around? So why is that happening? Because you are feeling your weight is slightly different. Okay. So now, when I write something like this, let's say here there is acceleration of the elevator, or your acceleration if you are riding on the elevator. Now let's suppose A is G. Let me write here so that we don't get confused. So when acceleration is equal to G, what's going to happen to the normal force? What are we seeing for the normal force when A is equal to Z? So when you replace this by, let's say, G, what's going to happen? So Neil is saying it's a 0, and so is Gabby. Are you guys seeing that 0 thingy? So G minus G means 0. So normal force 0. Your apparent weight is 0. What does it mean? You feel weightless. You feel weightless. So the astronomer inside the International Space Station, they are in free fall. Their acceleration is equal to G at that point. Okay. Yes, of course, G changes with time, height, but they are in free fall. So for example, if you were to jump off the roof, so when you are in the air, you're going to feel weightless. I'm not asking you to do that. Don't do it. Okay. But just saying. So your apparent weight is 0. You feel weightless. So that's what called weightlessness. Okay. So we have a weight when we are not accelerating, and we have apparent weight when we are accelerating. Okay. So what was the answer for this? Was that C? Accelerating up? Yes. So that was the answer. Okay. Oh. So it looks like we're gonna just leave it here today because it's 1:50. I do not want to take your extra time here, but if you like, you can try this problem. Okay, so far we looked at up and down. Now this is going to be sideways. So up and down, sideways, and incline. Those three kind of motion you want to learn. In that situation you want to use. You want to learn how to use Newton's laws. Okay, sideways, up and down, and incline plane. Okay, so this sideways is like a up and down. Not much a difference. There is acceleration. But backward force, forward force in the car, remember, is the force from the road that drives the car. So keep that in mind while drawing free body diagram on the car. So you need to draw a free body diagram of the car. So that means you need to draw forces acting on the car, not on the road. Okay. So with that said, I'm going to say bye-bye. Have a nice weekend, and I'll see you next week. Okay. And if you have any question, feel free to ask me. I'm going to be here if you need to, if you have question, because I don't have another class right away today. Oh, I have office hour today, Thursday. Yes. And that's going to be on another Zoom. So feel free to join during the office hour as well. Okay. Yes, I have office hour, but the Zoom ID is different.